Yeah.
Welcome to our presentation. My name is Sofia Hadir, and together with my colleague Gina Lopez, we will present our work on studying the effect of nutrient limitation on shoot and root growth, root morphology, and root topology of sugar beet and winter wheat under field conditions. In agriculture, fertilization management as well as liming are key for high yields and soil fertility, especially in organic farming and in low input agriculture. A high efficiency of nutrient acquisition by roots is the only way to cope with deficiencies. That's why a better understanding of the root-soil interactions plays a central role in growing crops in soils with low nutrient availability. Nutrient acquisition by roots is among the most important root properties, and to date there is still lack of information about the effect of nutrient omissions on the roots and their field scale. Root phenotyping allows to study the root-soil interactions, and there is also an increased demand for good quality phenotyping, which can serve both genomics and modeling. Also, the development of image analysis systems give insights on the hidden parts of the crops. The main objectives of our study is to investigate the effects of nitrogen, phosphorus, potassium, and liming omission on shoot and root growth of sugar beet and of winter wheat. And the second main motivation is to study the effects of fertilization on the root morphology and also topology using 2D image analysis systems.
This study was conducted in the Decob sub of long-term fertilizer experiment, which was established in 1904 near Cologne. This is one of the 10 oldest field experiments worldwide. The soil in Decob sub is happily alluvial soil, derived from the lowest 5-year crop rotation. This 5-year crop rotation was performed with sugar wheat, winter rye, fodder legume, and oat, that was replaced by potato in 1953. The crop management is characterized by the mineral fertilization of nitrogen, phosphorus, potassium, liming, and farm-dried manure. The experiment in Decob sub is not randomized block design and comprises 7 treatments: full fertilization plus manure and plus supplement mineral fertilizer, and treatment with omission of nitrogen, phosphorus, potassium, and liming, and another treatment of not fertilized at all. Notice that here that the underscore stands for the omission of the corresponding nutrient. In the treatment with a manure, this was applied after harvesting of the preceding crop at average of rate of 12 tons per hectare per year, with a dry matter content about 20%. The blue rectangle in the graph shows the place of the treatment for both sugar beet in 2019 and winter wheat for 2020. The sugar beet, the variety called BTS 7300N, was sown in April 2019 and harvested in the same year on November. For winter wheat, the variety called Boss was sown in December of 2019 and harvested in August of 2020. Regarding the shoot sampling and analysis, sugar beet was sampled 4 days to measure the dry matter, liver index, and nutrient content. On the other hand, the winter wheat was sampled 5 days to measure the plant height, dry matter content, liver index, and plants per square meter. To analyze the dry matter, the shoot fresh matter was oven dry at 105 degrees and weighted with a balanced estimated dry matter shoot weight. For the liver index, we use an area meter scanner. In the case of sugar beet, for the days 2 to 4, the root and shoot samples were milled, sieved, and analyzed with a total carbon and nitrogen with an elemental analyzer, and for phosphorus and potassium with a plate photometer. As an additional information, in this experiment, it also takes place a digital larger scale measurements through a UAV aircraft with a multispectral camera and red, green, and blue images. Those techniques allow to have a time series data of the crop phenology during the growing season. This technology applied to the agriculture is to contribute to the precision farming. But coming back to our experiment regarding to the root sampling and analysis, the sugar beets were buried out with a shovel on 4 days during the growing period, around 5 to 10 plants per treatment, with the surrounding soil to minimize the loss of roots. The extraction of the whole tuber was only possible at the first day. Later, the tuber and the first part of the top root was harvested and analyzed about first 30 to 40 centimeters, but not the whole deep root. The sugar beet roots were processed and single plants were scanned directly after harvest. In the case of roots of winter wheat, the plants were extracted twice with a root auger with a diameter of 10 centimeters and the length of 1 meter, as you can see in the photo above. The soil core was divided in pieces of 10 centimeters and each plot was taken for 4 replicates, 2 at the row and 2 between the rows. The soil samples were washed and sorted by hand. Later, the roots were scanned and finally converted to a digital information using the software WinReason to get the root morphology and root topology.
We come now to the results section. And in this slide, we present the mean values of shoot dry matter on the top and root dry matter in the bottom, as affected by the treatment and for the 3 last sampling dates. The treatment presents different values of root dry matter. The non-fertilized treatment is showing lower shoot dry matter than the fully fertilized with manure. And for example, in the 3rd sampling date, the nitrogen deficiency resulted in lower shoot dry matter, even lower than the non-fertilized treatment. We should also underline that the fully fertilized treatment experiences another stress that was not controlled in the experiment. And moving to the root dry matter, we can see in the graph that the nutrient deficiency impacted negatively the root dry matter, but it seems that the nitrogen limitation, for example, impacted much more the shoot part rather than the root part. Also, we can see that the plants reacted to deficiencies differently depending on the sampling date. This could be explained by the climatic conditions occurring in each sampling date. Below, we have a table that presents the fresh matter tuber yield. Even if it's widely recognized that for sugar beet crop, the most limited nutrient is nitrogen, however, here the lower yield was measured in the potassium deficient treatment. The highest tuber yield was, as expected, measured in the treatment fully fertilized with manure. We should also here say that the fully fertilized treatment show unexpected fresh tuber yield and also generally lower performance that start in the 2nd sampling date. We move now to the part of the root morphology of sugar beet. And to analyze the root morphology, we calculated the root length, the total root length of sugar beets during 4 sampling dates and for the 7 treatments. We should say that generally also here the root diameter show different trend depending on the growing stage. This could be explained by the water availability, but also by the turnover of fine roots. And generally, the stress related to nutrient deficiency enhanced the root length, as we can see it in the below graph. An advanced level of the morphology analysis constitutes the link analysis. It represents the study of each link, which is the root part between 2 forks or between a fork and the tip, regarding the morphology and also regarding the basic connectivity. The link analysis delivers many root parameters, as for example, the root length, the average diameter, also the projected area and the surface area. And to have a better understanding on the response of the shoot or rather root system to the nutrient deficiencies, we presented here the diameter classes as proportion from the total root length. And as we can see here, we have three classes: the very fine root class, diameter class, the fine root diameter class, and the medium to the coarse root diameter class. Here we can see that there was an increase of the very fine roots and decrease of the medium roots in nutrient limited conditions.
In this slide, we present some results for the shoot grow in the winter wheat. The graph above shows the shoot dry matter in grams, and in the 5 sampling dates shown in the x-axis. Each treatment is represented by a color. A similar analysis of the Liberia index is shown in the figure below at the same sampling dates. As we expected, we can see that the treatment of post-fertilization plus manure in the blue bar had the best performance in dry matter and Liberia index, while the not fertilization treatment in the brown bar computed the lower biomass and Liberia index. In the treatment with the one element omission, the mixed nitrogen treatment performed the lower values of biomass and Liberia index. In this slide, we present the result of the root length in the left side and the distribution of the roots by diameter of winter wheat in the right side. I have to mention that these are preliminary results because the washing and sorting process is not yet completed. That explains also the mixed P omission treatment in the analysis. In the graph of the root length, we can see how long the roots are according to different depths. So far, the results are unexpected since the treatment of full fertilization with manure and liming omission computed the longer root system. In the right graph, we present the distribution of the roots according to the diameter. In the y-axis shows the proportion of the root length and in the x-axis each treatment. The green bars are the medium roots with a diameter greater than 2 millimeters. The orange bar shows the fine roots with a diameter between 0.5 and 2 millimeters. And the purple bars represent a very fine roots with a diameter lower than 0.5 millimeters. In general, we find more very fine roots, but a smaller proportion of fine and medium roots in the unfertilized and potassium omission treatment. We will be able to have a better analysis when all the results are available. To sum up, we can say that we have a negative impact of the nutrient omission on the shoot growth parameters on fruit traits of both plants, both crops. The lowest tuber yield is depicted in the cow omission treatment and not fertilization. For sugar beet, plant enhanced the root shoot ratio as response of nutrient limitation, and the root length is enhanced as response to nutrient limitation, especially in the treatment without K and without P. Shoot and root parameters behave differently as function of the sampling date. In other words, as function of growing stage and climate conditions in the respective time. For winter wheat, the lowest shoot dry matter was depicted by the non-fertilization treatment. The full fertilization plus manure had the highest performance, and the nitrogen was the most critical element. All the treatment shows a greater presence of very fine roots, and the treatment of full fertilization plus manure, full fertilization, and nitrogen omission shows more medium roots. The wheat data is ongoing and has to be analyzed afterwards.
To conclude, we can say that a large data set was generated during both sampling campaign in 2019 and also 2020. And this large data set permits to investigate the soil-root interaction of two major crops and their field conditions. For the winter wheat, the results are preliminary and will be further improved in the next time. The study also gave a general insight into the effects of nutrient omissions on the root and shoot growth, root morphology, and root linking of sugar beet and their field conditions. It has been also shown that image analysis systems allow to investigate the below ground part of the crops. However, there are still some restrictions related to the method destructive used, since in our experiment only a certain depth could be investigated, for example, for sugar beet. So, further studies should focus on development methods for easier extraction of fine roots, namely in sugar beet. The effect or the fact of choosing single dates to make the sampling resulted in some constraint when trying to evaluate the results. Here, we can say that continuous measurement methodologies can improve the findings. Also, further studies should take into consideration the crop water uptake and the deeper root system when studying the effects of nutrient omissions on shoot and root drains. And thanks a lot for your attention.